You approach a neutron star gently, letting your mind adjust to the extraordinary conditions that define its existence. It is a remnant, born from the collapse of a star much larger than the Sun. When such a star exhausts its nuclear fuel, gravity overwhelms the outward pressure from fusion, compressing the core into a sphere only about 20 kilometers across. In this tiny volume, more mass than the Sun is compacted, resulting in an object with densities that are almost unimaginable. Each cubic centimeter contains more than 100 million tons of matter. You feel the immensity of this compression as you picture the familiar scales of everyday matter fading away into a realm where atomic nuclei themselves are pressed into near contact. Your mind lingers on the surface of this dense star. You consider the forces at play. Gravity is extraordinary here, so strong that a single teaspoon of neutron star material would weigh more than 1 billion tons on Earth. The escape velocity from the surface approaches 1/3 the speed of light. In such an environment, matter behaves differently than anything experienced on Earth. Electrons and protons have combined under pressure to form neutrons, leaving a composition that is almost entirely neutrons, with a thin layer of electrons and protons on the outer crust. You sense the remarkable uniformity of this structure and the way it challenges conventional understanding of matter. The magnetic field of a neutron star extends far into space, millions to trillions of times stronger than the magnetic fields we are familiar with on Earth. You imagine tracing these lines gently around the star, feeling how charged particles spiral along the field. These fields influence the motion of plasma and charged particles nearby, accelerating them to extremely high energies. Some neutron stars, called pulsars, rotate rapidly, sweeping their magnetic beams across space. With rotations ranging from once every few seconds to hundreds of times per second, the beams create pulses detectable across vast distances. You notice how the regularity of these pulses provides astronomers with natural clocks, precise enough to measure subtle changes in orbital motion, gravitational waves, and even tests of general relativity. You let your attention settle on the surface and the crust beneath. This outer layer, only a few kilometers thick, is composed of tightly packed nuclei arranged in crystalline lattices. Underneath, the density rises sharply and nuclei deform under pressure, forming elongated or pasta-like structures due to competing nuclear and gravitational forces. These formations are named for their resemblance to earthly shapes, yet they are fully grounded in nuclear physics. The conditions in this crust are extreme. Pressures are billions of times higher than anything you could produce on Earth, and the temperature can be millions of degrees in young neutron stars, gradually cooling over time. You sense how these layers, though invisible to your eyes, are mapped in detail through theoretical models and observational evidence, such as X-ray emissions and thermal radiation. As you observe the neutron star's rotation, you notice how even the slightest irregularities, known as starquakes, release energy. The crust may crack under stress, emitting bursts of X-rays or gamma rays, evidence that the star is not entirely static. These changes can be tiny, yet they reveal the internal structure and rigidity of the star. You recognize that the dynamics of the crust and the interactions between neutrons, protons, and electrons define phenomena such as glitches, sudden increases in rotation speed. These events allow astronomers to infer the properties of matter under extreme density, shedding light on nuclear physics that cannot be replicated on Earth. You feel the vast gravitational influence extending beyond the neutron star itself. Its gravity affects nearby matter, drawing in gas from companion stars if one exists, forming accretion disks. In these disks, matter spirals inward, heating up to millions of degrees, emitting X-rays and other high-energy radiation. You follow the paths of individual particles in this flow, understanding how angular momentum and magnetic fields shape their motion. Occasionally, matter can escape along magnetic poles in the form of relativistic jets, observed across many wavelengths. These processes offer scientists a laboratory to study high-energy astrophysics and plasma physics in ways that terrestrial experiments cannot achieve. Your gaze drifts to the motions of neutron stars within binary systems. Many neutron stars exist paired with other neutron stars, white dwarfs, or normal stars. Their orbits can be measured precisely through pulse timing or gravitational interactions. You notice how the gravitational pull from these companions influences the neutron star, creating tidal forces that slightly distort its shape. Over time, such forces can affect the orbit, causing it to decay gradually. Observations of these systems provide some of the most compelling evidence for gravitational wave emission, confirming predictions from general relativity. You sense how these delicate orbital dances, invisible to the naked eye, are mapped carefully by astronomers through patient observation over decades. You consider the radiation environment surrounding the neutron star. Magnetic fields accelerate electrons to near light speeds, producing synchrotron radiation, which can be detected as radio waves, X-rays, or gamma rays. The surface temperature, while cooling over millions of years, still produces thermal X-rays that reveal information about the star's size, mass, and composition. You appreciate the careful measurements astronomers make, combining observations across multiple wavelengths to reconstruct a complete picture of these dense objects. Each photon, each pulse provides a data point that tells a story about the extreme physics at play. Your mind lingers on the concept of density and pressure at the core. Beyond the crust, the interior may consist of a superfluid of neutrons, where frictionless flow occurs and protons form superconducting phases. These exotic states of matter are inferred from theoretical models constrained by observational data, such as the maximum observed masses of neutron stars and the behavior of pulsar glitches. You reflect on how these interiors challenge and expand your understanding of fundamental physics, linking astronomical observations to nuclear theory and quantum mechanics. Finally, you absorb the quietness surrounding the neutron star. Despite its extreme properties, it exists in relative solitude, a silent sentinel in the galaxy. Its magnetic fields, rotation, and dense matter set the conditions for dramatic events in the future, such as mergers with other neutron stars. These objects, though extreme, are predictable in many ways, their behavior encoded in the laws of physics. You feel the patience required to study them, the slow accumulation of knowledge over decades, and the precise instruments that allow us to witness these phenomena. The vast densities, powerful magnetic fields, and precise rotations all combine to make the neutron star a laboratory of extreme physics, quietly existing in space while providing essential clues to understanding the universe. Even in stillness, it contains the potential for future cosmic events that shape the distribution of elements, send ripples across spacetime, and connect fundamental forces in ways observable across light years. Observing the stability and subtle motions of the star allows you to anticipate the delicate interactions that will eventually lead to encounters with a companion, sending gravitational waves and high-energy radiation outward, carrying knowledge of the universe's most compact objects. You focus on a pair of neutron stars locked in a gravitational embrace, orbiting each other with precise regularity. Each completes a full rotation around their shared center of mass in mere hours, yet their motion is imperceptible to the human eye at vast distances. The pull between them is immense, each star tugging on the other with forces far beyond anything experienced on Earth. You sense the invisible threads of gravity stretching across space, holding the stars in a delicate, unbroken orbit. Over time, these threads ripple outward as gravitational waves, tiny distortions in spacetime itself, carrying energy away from the system. You follow the path of the stars as their orbital motion gradually decays. The energy lost through gravitational waves is minuscule in the short term but accumulates steadily over millions of years. Observations of binary pulsars, particularly the Hulse-Taylor system discovered in 1974, confirm this slow decay with astonishing precision. You feel the passage of time differently as you imagine decades of careful radio observations, measuring the slight decrease in orbital period and verifying predictions made by Einstein's equations. The orbit shrinks imperceptibly, drawing the stars ever closer in a quiet, measured dance. Your attention rests on the mechanics of the orbit. The stars move in elliptical paths, with their velocity increasing as they approach each other during the closest part of the orbit, known as periastron. Tidal forces subtly deform the stars, stretching them along the axis facing their companion. These deformations affect the distribution of mass and, in turn, the emission of gravitational waves. You observe how even tiny asymmetries in shape and motion influence the strength and frequency of the waves, providing scientists with detailed information about the masses, radii, and internal structures of the stars. The concept of gravitational radiation becomes tangible as you follow these ripples spreading through space. Gravitational waves propagate at the speed of light, stretching and compressing space in perpendicular directions. You imagine the waves passing through the cosmos, imperceptible to human senses, yet detectable by extraordinarily sensitive instruments on Earth. LIGO and Virgo measure changes in distance smaller than a fraction of a proton's width, revealing the passing of these waves from distant binary neutron stars. Each oscillation carries a message about the orbit, the masses of the stars, and the energy lost from the system. As the stars spiral inward, their orbital period decreases, causing them to move faster and faster. This acceleration increases the frequency and amplitude of the gravitational waves, a process observable as a chirp when detected on Earth. You consider the remarkable precision required to capture these signals, and how these observations provide the first direct confirmation of gravitational waves in 2015, nearly a century after they were predicted. You feel the subtle beauty of this slow acceleration, a natural consequence of energy loss, perfectly following the equations of general relativity. Your mind lingers on the scale of time involved. From the perspective of human history, the inspiral is nearly eternal. Millions of years may pass while the stars move imperceptibly closer, their gravitational energy gradually converted into spacetime ripples. You sense the patience of the universe, a process so slow that a single human lifetime cannot perceive significant changes, yet so precise that astronomers can track them over decades. You appreciate the quiet rigor of these natural phenomena, unfolding in cosmic silence, obeying laws that remain consistent across space and time. You examine the tidal interactions in more detail. As the stars approach, each experiences a stretching along the axis toward the other, and a slight compression along perpendicular directions. This deformation stores gravitational potential energy and changes the distribution of mass within each star. You consider how these tidal effects alter the orbital dynamics subtly, producing precession and resonance effects. Observations of pulsar timing variations and theoretical simulations allow scientists to reconstruct these interactions, improving estimates of the star's internal composition and stiffness, providing insight into the equation of state for neutron-rich matter. Your attention shifts to the role of spin. Each neutron star may rotate rapidly on its own axis, from a few times per second to hundreds of times per second. These spins interact with the orbital motion, affecting the gravitational wave emission and the eventual merger dynamics. You visualize how aligned spins can slightly prolong the inspiral, while anti-aligned spins can accelerate the process. By studying these effects in detected signals, astrophysicists can infer the rotational properties of the stars before they collide, combining timing data, waveform analysis, and theoretical models. The environment surrounding the binary system is not empty. Remnants of supernovae, interstellar gas, and occasional accretion from a companion may form a tenuous disk around the neutron stars. While this matter is sparse compared to the stars themselves, it interacts with magnetic fields and radiation, producing weak emissions detectable by sensitive telescopes. You feel the interconnectedness of these processes, where even the surrounding medium responds to the gravitational presence of the stars, offering additional observational clues for scientists to piece together the story of the inspiral. You reflect on the predictability of this slow spiral. The laws governing the motion, the emission of gravitational waves, and the internal responses of the stars are all well understood, confirmed by decades of observation and simulation. You sense the reliability of the underlying physics, which allows astronomers to forecast the timing and characteristics of eventual mergers, even when they occur millions of years in the future. The stars move with quiet certainty, following the precise rhythms dictated by gravity and relativistic effects. Your attention rests on the energy balance. As gravitational waves carry energy away, the star's kinetic and potential energy adjusts accordingly. The orbit tightens, the velocities increase, and the system radiates increasingly higher frequency waves. You feel the inevitability of the process, the slow compression and acceleration preparing the stars for the dramatic interaction that will occur once they are sufficiently close. This transfer of energy is imperceptible to any nearby observer, yet it drives the entire inspiral, shaping the star's fate with precise consistency. Finally, you consider the human perspective. From Earth, the inspiral is observed indirectly through pulsar timing, gravitational wave detectors, and theoretical simulations. These observations confirm decades of predictions and provide a roadmap for understanding how neutron star binaries evolve. You appreciate the patience and precision required to detect the faint signals of spacetime ripples and the careful calculations that allow scientists to trace the slow dance of these massive, dense objects across the galaxy. Even in the absence of collision, the inspiral itself is a profound expression of gravity and relativity, a slow-motion ballet where energy is transmitted across the universe in waves, imperceptible yet measurable. The steady approach of the two stars, governed by precise physical laws, is a reminder of the quiet processes that shape cosmic evolution, setting the stage for events that will release tremendous energy, forge new elements, and ripple through spacetime in ways detectable across vast distances. You begin by imagining spacetime as a flexible fabric, responding to the motion of massive objects. When two neutron stars orbit each other, their immense masses create tiny oscillations that ripple outward at the speed of light. These ripples, known as gravitational waves, are subtle distortions in the distances between points in space. As you picture them spreading, you realize that every oscillation carries information about the binary system, the mass of each star, the shape of its orbit, and even the internal structure that affects tidal interactions. The concept of gravitational waves was predicted by Einstein in 1916 as a natural consequence of his general theory of relativity. You reflect on how these waves represent energy carried away from a system in motion, in this case, the orbiting neutron stars. For decades, their existence remained theoretical, as the amplitude of these waves is extraordinarily small. Measuring the fractional stretching and compression of space by just a fraction of a proton's width requires instruments of unprecedented sensitivity. You appreciate the ingenuity that allows human technology to detect these faint signals across the vastness of the cosmos. You focus on the waves themselves. As the stars move closer together, the frequency of emitted waves increases. The pattern of these oscillations, often called a chirp, rises in both frequency and amplitude, encoding a precise record of the inspiral. Each ripple represents a minuscule change in the distance between points in space, stretching one direction while compressing another. These changes are perpendicular, propagating through space without the need for any medium, revealing the elasticity of spacetime itself. You sense the elegance of this phenomenon, entirely determined by the masses, distances, and motions of the stars. Observatories like LIGO in the United States and Virgo in Europe are designed to capture these waves. You visualize their long perpendicular arms, lasers reflecting between mirrors, measuring length changes smaller than 1,000th the diameter of a proton. When a gravitational wave passes through, the interference pattern of the reflected light shifts slightly, signaling the arrival of a wave. You understand that these signals are fleeting and require careful analysis to distinguish them from background vibrations caused by Earth's environment, such as seismic activity, human activity, or thermal noise. The precision and patience of scientists allow them to extract the faint whispers of spacetime from this noise. You consider the information encoded in a gravitational wave. The amplitude reveals the distance to the source. Stronger waves indicate closer or more massive systems, while weaker waves originate from farther away. The frequency tells the orbital period of the binary, showing how fast the stars are moving. The shape of the waveform carries clues about the masses of the neutron stars and the alignment of their spins. You feel how each subtle feature is a natural record of the dynamics of the system, an unreadable story that scientists decode with sophisticated models and computer simulations. As you follow the waves traveling outward, you notice how they interact minimally with matter. Unlike light or particles, gravitational waves pass through gas, dust, and even entire galaxies with almost no interference. This allows them to carry pristine information across billions of light-years. You feel a sense of clarity as these waves transmit an unaltered record of extreme events, offering insights into regions of the universe that are otherwise opaque, such as the interiors of neutron stars and the moments just before collisions. You contemplate the scale of detection. The events that generate detectable waves occur in distant galaxies, often hundreds of millions of light-years away. Yet, instruments on Earth can capture the tiny distortions caused by these distant collisions. Each detection confirms predictions from general relativity and provides empirical measurements of astrophysical phenomena. The universe, though vast, is connected through these ripples, allowing you to hear the motion of massive stars long after the events themselves have occurred. Your attention moves to the binaries in spiral and the evolution of the waveforms. As the stars orbit closer, gravitational waves increase in frequency and amplitude. You notice how the final moments before collision produce the strongest signals. The waveform rises in a predictable pattern, giving scientists a countdown to the merger. Observations of such signals, including the landmark detection of GW 170817 in 2017, have confirmed both the existence of gravitational waves and the models of neutron star and spirals developed over decades. You sense the precision of nature, revealing itself through predictable patterns detectable across the cosmos. You reflect on the multi-messenger approach. Gravitational waves are one channel of information, complementing electromagnetic observations. For the same neutron-star merger, gamma rays, X-rays, optical light, and radio waves can provide additional insights into the ejected material, nucleosynthesis, and remnant formation. You feel the interconnectedness of these observations, each wavelength and wave type offering a different perspective on the same event. Gravitational waves provide the timing and mass information, while light reveals composition, temperature, and expansion dynamics. Together, they allow a complete reconstruction of the collision. The waves also carry information about the geometry of space and the universe's expansion. By measuring the amplitude and frequency of signals from multiple mergers, scientists can estimate distances and calibrate cosmological models. You consider how the detection of these ripples contributes to understanding the Hubble constant and the rate at which the universe expands. The same gravitational waves that reveal the details of a binary neutron star system also provide a natural probe of the cosmos on the largest scales. You sense the patience required to interpret these signals. Each waveform must be matched to theoretical templates generated through numerical relativity, simulating the behavior of neutron stars under extreme gravity. Small differences in mass, spin, and equation of state produce subtle changes in the waveform, which scientists can decode to infer the physical properties of the stars. You feel the precision of this work, each gravitational wave offering a direct line of evidence for the behavior of matter under conditions that cannot be reproduced on Earth. Even as you observe the distant sources, you recognize the universality of the physics. Gravitational waves obey the same principles whether they originate from neutron stars, black holes, or other massive objects. Their behavior is predictable, confirmed repeatedly, and provides a bridge between theory and observation. You sense the calm consistency of the universe, where these ripples carry messages across space and time, faithfully conveying information about extreme processes in a language written in the fabric of spacetime. The faint stretching and compressing of space, imperceptible to human senses yet measurable with extraordinary technology, reminds you of the quiet power of gravity. These waves link distant events to local detectors, bridging vast distances. You follow them as they propagate outward, carrying a record of orbital motion, energy loss, and relativistic interactions. Each oscillation is a testament to the predictive success of Einstein's theory and the careful observation that allows humans to witness phenomena billions of light-years away. You observe the neutron stars as their orbital separation becomes smaller with each revolution. The dance that began millions of years ago has entered its final, rapid stages. Their motion accelerates dramatically as they draw closer, moving at a significant fraction of the speed of light. You notice how the frequency of gravitational waves rises, producing a sharp, steadily increasing chirp detectable across the universe. The energy carried away by these waves grows, and the star's gravitational pull becomes almost impossible to resist. Time itself feels different here, as the spiral progresses in a swift, accelerating rhythm. Your attention rests on the shape of the stars. Tidal forces stretch each star along the axis pointing toward its companion, producing elongated, slightly asymmetric shapes. These deformations affect the distribution of mass within the stars, subtly altering the gravitational field and the emission of waves. You sense how every movement, every deformation, is precisely governed by the laws of physics, and how simulations allow scientists to predict the behavior of these dense, rapidly moving objects. Small asymmetries in the stellar shapes contribute to the overall gravitational signal, revealing details about internal structure and the equation of state of neutron-rich matter. The rotation of the neutron stars also becomes significant. If the stars were spinning prior to this phase, their spins interact with the orbital motion. Depending on their alignment, the spins can slightly speed up or slow down the final inspiral. The stars may also begin to synchronize, gradually aligning rotational periods with the orbit due to tidal interactions. You notice how these rotations, though invisible to the naked eye, play an essential role in the dynamics of the merger and the resulting distribution of matter and energy. You become aware of the forces acting at the surface. The crust experiences immense stress from tidal deformation, and in some cases, it may crack or yield under pressure. These starquakes can release bursts of energy, predominantly in the form of high-frequency gravitational waves and potentially electromagnetic signals. You imagine how subtle this energy release may be compared to the total gravitational energy, yet how it is detectable by precise instruments and contributes to a detailed understanding of the star's structure. The space around the stars is filled with electromagnetic and particle interactions. Magnetic fields, already intense, stretch and twist as the stars approach. Charged particles trapped along these field lines accelerate, generating radiation that may be observed across the electromagnetic spectrum. You consider the rapid amplification of magnetic fields due to differential rotation, turbulence, and compression, creating a complex environment immediately surrounding the merging objects. Simulations predict the formation of highly energetic magnetospheres, which influence both matter and radiation during the final seconds. The interior of each star is a realm of extreme physics. Neutrons, arranged in a superfluid state, move with almost no friction. Protons and electrons form superconducting currents that interact with the intense magnetic field. You reflect on how these internal states respond to tidal stresses and accelerations, affecting the star's moment of inertia and rotational behavior. The properties of this ultradense matter are inferred from careful modeling, constrained by observational evidence from pulsar timing, gravitational waveforms, and X-ray emissions. These models allow predictions of how the final inspiral unfolds and how the stars will deform, oscillate, and ultimately coalesce. You notice the acceleration of the inspiral. Each orbit takes less time than the previous one, producing gravitational waves with increasing frequency and amplitude. The binary system emits enormous energy, tens of % of the sun's total energy output over its lifetime, concentrated into the final moments. You sense the inevitability of this process, dictated by general relativity, where energy is radiated through spacetime in a coherent, predictable pattern. The motion of the stars follows precise relativistic equations, allowing scientists to anticipate the waveform that will be detected by instruments on Earth. You reflect on the emission of neutrinos. As the star's outer layers heat under extreme compression and shear, nuclear reactions generate vast numbers of neutrinos, nearly massless particles that escape freely from the dense matter. Neutrinos carry away energy, contribute to the cooling of the merging matter, and encode information about the extreme densities and temperatures at the star's surfaces. Observations of neutrino bursts from such events, while challenging, provide additional confirmation of models predicting energy release, composition, and dynamics during the final inspiral and immediate aftermath. The surrounding space is prepared to respond. Any low-density gas or debris from prior accretion forms a tenuous environment, ready to interact with the energetic outflows. You consider how even sparse matter can absorb energy, produce radiation, and reveal information about the collision indirectly. This environment contributes to the multi-messenger picture that astronomers assemble, combining gravitational wave data, gamma rays, X-rays, and optical observations to reconstruct the full dynamics of the merger. You sense the intricate connections between the stars, their surroundings, and the signals that travel across light years to reach Earth. As the stars approach the final moments before contact, their oscillations intensify. Each neutron star vibrates under tidal stress, producing subtle variations in gravitational wave emission. These oscillations encode information about the star's internal stiffness and the equation of state of ultradense matter. You feel the precision with which physics predicts these vibrations and the remarkable accuracy of the numerical simulations that reproduce them. Observations of gravitational waves allow scientists to confirm these predictions, providing a rare window into physics that cannot be replicated in any terrestrial laboratory. You focus on the energy scales involved. The orbital energy, gravitational potential energy, and rotational kinetic energy combine to form a nearly unimaginable total. As the stars close in, these energies are converted into gravitational waves, high-energy photons, and particle emissions. The system becomes a reservoir of potential observable phenomena, each component carrying precise information about the mass, spin, and internal structure of the stars. You notice how the universe records these extreme processes across multiple channels simultaneously. Even as the motion accelerates, the process remains predictable. General relativity governs the trajectory, tidal deformations, and gravitational radiation with remarkable precision. Each orbit, each oscillation, follows the laws of physics without deviation. You sense the calm regularity underlying what appears, from a human perspective, as dramatic. The gradual, steady buildup of energy, culminating in the final approach, is a natural consequence of mass, gravity, and spacetime interacting in accordance with well-understood principles. You observe the moments just before the merger. Distances shrink to tens of kilometers, velocities reach significant fractions of light speed, and gravitational waves surge in amplitude and frequency. The star's magnetic fields, crustal deformations, and internal superfluid motions all contribute to the signals that propagate outward. Neutrinos, photons, and gravitational ripples carry complementary information, recording the final dynamics with exceptional fidelity. You feel the extraordinary scale and precision of these interactions, a prelude to the transformation that will follow when matter merges under extreme conditions. In these last seconds, the system is a remarkable combination of extremes: densities beyond nuclear magnetic fields trillions of times stronger than Earth's, velocities approaching light speed, and energy release on scales larger than entire galaxies produce in a second. Yet, the evolution remains governed by clear physical laws, predictable in principle, and measurable through careful observation. You sense the preparation for the dramatic transformation, the conversion of orbital motion into radiation, matter ejection, and the potential formation of a new, even denser remnant. You watch as the two neutron stars converge, the space between them vanishing almost instantaneously. The final orbit compresses to mere kilometers, and velocities approach a significant fraction of the speed of light. The gravitational waves emitted in the preceding in-spiral surge to their peak amplitude, carrying enormous energy outward. You sense the universe holding its breath as the stars collide, each a mass greater than the sun, yet confined to the size of a city. The collision itself is a complex sequence of physical interactions. The crusts of the stars are shattered, releasing enormous pressure and heat. Shock waves propagate through the neutron-rich matter, creating temperatures of billions of degrees. These shocks accelerate particles and produce bursts of radiation across the electromagnetic spectrum. You observe that the energies involved are comparable to the total energy output of the sun over billions of years, concentrated into a volume smaller than most cities. The density, pressure, and temperature are extreme, producing conditions unreachable by any terrestrial experiment. Matter begins to mix violently as the cores interact. Neutrons, protons, and electrons are redistributed under tidal forces and immense gravitational stress. Some matter is ejected at relativistic speeds, forming a rapidly expanding cloud. This ejected material, moving outward into surrounding space, becomes the seed for heavy element formation. You follow the motion of individual components, noting how the interplay between gravity, pressure, and nuclear interactions governs the dynamics of the merger. The motion is not chaotic but follows predictable physical laws, even in the apparent violence of the collision. The central remnant depends on the combined mass of the stars and the equation of state of neutron-rich matter. If the remnant is below a critical mass, It may temporarily form a hypermassive neutron star, supported by differential rotation and thermal pressure. Otherwise, the remnant collapses promptly into a black hole. You sense the transformation of matter into extreme states, the formation of a horizon if a black hole emerges, and the way gravitational energy is redistributed into space, light, and neutrinos. As the cores merge, gravitational waves continue to radiate outward, but their pattern shifts. The inspiral chirp transitions into a complex, high-frequency waveform. You notice the signal contains information about the violent redistribution of mass, the onset of turbulence, and the brief oscillations of the hypermassive neutron star if one forms. These features allow scientists to infer the remnant's properties and the nature of ultradense matter. You appreciate the precision of this cosmic record, encoded in ripples traveling across light years. The ejected matter is a focus of intense transformation. Shock heating drives rapid nuclear reactions, particularly R-process nucleosynthesis, forming heavy elements such as gold, platinum, and uranium. You observe how the material is launched at significant fractions of the speed of light, expanding and cooling as it moves outward. The composition of this ejecta is determined by density, temperature, and neutron richness, all predictable from simulations and constrained by observations of electromagnetic counterparts to neutron star mergers. Gamma rays are emitted within seconds of the collision. These bursts, highly collimated in some cases, signal the acceleration of particles and the formation of relativistic jets. You sense the synchronization between gravitational wave signals and gamma-ray emission, confirming the connection between the compact binary merger and short gamma-ray bursts. The high-energy photons travel across the universe, providing independent confirmation of the collision and allowing astronomers to triangulate the event with gravitational wave detectors. Neutrinos, almost massless and weakly interacting, escape from the hot, dense matter with minimal obstruction. They carry away energy and information about the interior conditions of the merger. Observing these particles is challenging, yet they provide crucial insight into the physics at play during the collision. You reflect on how each messenger, gravitational waves, light, and neutrinos, offers complementary information, allowing a comprehensive reconstruction of the merger dynamics. Magnetic fields are amplified dramatically during the collision. Differential rotation and turbulence stretch and twist the field lines, generating strengths trillions of times greater than Earth's magnetic field. These fields influence the motion of charged particles, the structure of jets, and the distribution of ejected matter. You follow the interactions between magnetism and matter, understanding how simulations model these complex dynamics to predict observable signatures in both radiation and particle outflows. The remnant core, if it forms a hypermassive neutron star, undergoes oscillations. These vibrations radiate energy in gravitational waves and modulate the emission of light and particles. You notice how the oscillation frequencies depend on mass, radius, and the internal stiffness of neutron-rich matter, allowing scientists to probe the physics of matter at densities beyond the nuclear scale. Each pulse of radiation, each ripple of spacetime, carries a precise imprint of the conditions inside the remnant. The surrounding environment absorbs some energy from the ejecta. Any interstellar gas or previous debris interacts with the outflow, producing shocks and additional electromagnetic emission. Observing these interactions provides further information about the speed, composition, and distribution of the matter expelled by the merger. You feel the interconnection between the merger and its broader cosmic neighborhood, as even sparse surrounding matter responds to the tremendous energy released. Energy conservation remains central. The gravitational potential energy and orbital kinetic energy are redistributed into ejected matter, radiation, neutrinos, and gravitational waves. You follow the balance carefully, seeing how nearly half of the orbital energy can be radiated away in gravitational waves during the final moments. The remainder contributes to heating, particle acceleration, and the formation of the remnant. You sense the elegance of physics in action, with every component traceable and measurable. You observe the formation of relativistic jets in some scenarios. These narrow streams of material accelerate to speeds approaching light, carrying enormous kinetic energy. Their direction and structure depend on the angular momentum and magnetic field geometry of the merging system. When aligned with Earth, these jets are detected as short gamma-ray bursts, confirming the violent nature of the collision. You appreciate the coordination between simulation, observation, and theory that allows scientists to link jets, gamma rays, and gravitational waves to a single astrophysical process. The thermal radiation from the merger contributes to a kilonova, a luminous optical and infrared transient. You watch the ejected matter expand, cool, and produce light over days and weeks. The brightness and color of the kilonova depend on the composition of the ejecta, particularly the abundance of heavy R-process elements. Observations of such events, combined with gravitational wave data, provide direct evidence for nucleosynthesis occurring in neutron star mergers. You sense the profound connection between microscopic nuclear processes and observable cosmic phenomena. Even in the extreme violence of the collision, physical laws govern every interaction. General relativity dictates gravitational dynamics, nuclear physics describes matter behavior, and electromagnetism guides charged particles. You notice the predictability in the apparent chaos, the way simulations reproduce the observed signals with remarkable accuracy. The collision is both cataclysmic and precise, a natural consequence of mass, energy, and spacetime interacting under the universal laws. The universe receives the full spectrum of the event. Gravitational waves ripple outward, gamma rays streak across space, neutrinos scatter through the cosmos, and heavy elements are ejected to seed future stars. You feel the coordination of these processes, each leaving a measurable imprint on the surrounding universe. These signals allow scientists to reconstruct the dynamics with incredible detail, connecting theoretical predictions to empirical evidence. You watch the ejected matter from the neutron star collision expand rapidly into space. The material, rich in neutrons, is initially dense and hot, with temperatures reaching billions of degrees. Shock heating and radioactive decay energize the matter, causing it to emit light across the electromagnetic spectrum. You notice the process is gradual, with the luminosity peaking over hours to days as the cloud cools and expands. The term kilonova describes the brightness, roughly 1,000 times that of a typical nova, yet far dimmer than a supernova. The composition of the ejected matter is remarkable. The neutron-rich environment drives rapid neutron capture, known as R-process nucleosynthesis. You follow the sequence in which neutrons are added to seed nuclei faster than they can decay, forming extremely heavy elements. These reactions produce stable isotopes of gold, platinum, uranium, and other rare elements, dispersing them into the surrounding space. You sense how nuclear physics, applied in this extreme cosmic laboratory, explains the origin of many of the heavy elements found on Earth. As the ejecta expands, its density decreases, allowing photons to escape more easily. The opacity of the material depends on its composition. Elements with complex electron structures, such as lanthanides, absorb and re-emit light, affecting the observed color of the kilonova. Initially, the emission may appear blue, dominated by lighter elements, then gradually shifts to red as heavier elements dominate. You notice how careful observation of these color changes provides direct insight into the types of elements synthesized during the merger. You follow the energy source of the light. Radioactive decay of unstable nuclei produces heat, which powers the emission of photons. Each decay releases energy in the form of gamma rays and kinetic energy of particles, warming the ejecta. This process continues over days, providing a sustained light curve that can be observed from Earth with telescopes sensitive to optical and infrared wavelengths. You appreciate how astronomers can measure the light curve and infer the amount, velocity, and composition of the ejected material. The speed of the ejecta is extraordinary. Material moves outward at 10 to 30% of the speed of light, shaped by tidal forces, shocks, and magnetic fields. You imagine the cloud as a rapidly expanding shell, with internal gradients in density and composition. Simulations reproduce these dynamics, showing that different parts of the ejecta may contain varying element abundances and velocities. Observing these patterns helps scientists reconstruct the geometry of the explosion and the processes that drive element synthesis. You notice the observational breakthroughs that kilonovae have provided. The event GW 170817, detected in 2017, produced both gravitational waves and a kilonova visible in optical and infrared telescopes. Observations matched theoretical predictions, confirming that neutron star mergers are significant sources of heavy elements in the universe. You reflect on the combination of data. Gravitational waves provided timing and mass information, while electromagnetic signals revealed composition, velocity, and luminosity. Together, these measurements offer a complete picture of the astrophysical processes at work. The spectra of the kilonova carry detailed information. Specific absorption and emission lines correspond to different elements formed during nucleosynthesis. You follow how scientists identify signatures of lanthanides and actinides in the infrared, confirming the presence of some of the heaviest naturally occurring elements. By comparing observations with simulations of nuclear reactions, researchers refine their understanding of the physical conditions inside the merger and improve models of neutron-rich matter. You observe the distribution of elements. The high-speed ejection spreads matter into surrounding space, where it eventually mixes with interstellar gas. This material contributes to future generations of stars, planets, and even life, providing the raw elements for chemistry. The kilonova, therefore, is not only a spectacular display of light, but also a process of cosmic recycling, distributing newly formed heavy nuclei throughout galaxies. You sense the continuity of physical processes, from nuclear reactions in stellar remnants to the formation of elements in distant worlds. The luminosity of the kilonova evolves predictably. Initially, photons escape from the outer layers, producing a brief, blue peak. Over several days, photons from deeper layers diffuse outward, and the emission reddens due to higher opacities from heavy elements. You notice how models of radiative transfer match observations, providing a direct link between theory and empirical evidence. Each light curve carries encoded information about mass, composition, and expansion speed, offering astronomers a laboratory for studying extreme physics beyond Earth's reach. Magnetic fields also influence the kilonova emission. They help channel some of the ejecta into collimated flows, affect particle acceleration, and guide the escape of high-energy radiation. You consider how simulations incorporate these fields to predict the anisotropy of the emitted light, revealing the orientation of the merger relative to Earth. Observational data confirm these predictions, demonstrating the interplay between gravity, nuclear physics, and electromagnetism in shaping cosmic events. The interplay of radioactive heating and expansion ensures that kilonovae remain visible over timescales of days to weeks. You follow the gradual fading, as photons lose energy and the ejecta cools. This temporal evolution provides information about both the total mass of ejected material and the types of isotopes synthesized. Each data point offers a snapshot of nuclear reactions occurring under extreme conditions, inaccessible in laboratory settings. You sense the quiet precision with which the universe records and reveals its processes. Even as the kilonova dims, the material continues to expand and mix with interstellar gas. Future generations of stars will inherit these heavy elements, and over billions of years, they will become part of planets, asteroids, and even the building blocks of life. You appreciate how the immediate brilliance of a kilonova connects directly to the long-term chemical evolution of galaxies. The physical laws governing the merger, radioactive decay, and photon diffusion operate consistently, linking events across scales of time and space. Observing a kilonova from Earth requires careful coordination. Telescopes across the globe, from optical to infrared, capture the fading light, while gravitational wave detectors provide the timing and location. You reflect on the precision and international cooperation that allows scientists to detect these rare, transient events. Each observation adds to the collective understanding of how the universe synthesizes heavy elements and distributes them through space. You sense the lasting significance of kilonovae. Beyond their visual spectacle, they confirm fundamental predictions about nucleosynthesis, gravitational wave counterparts, and the physics of ultradense matter. The event illuminates the connections between nuclear processes, stellar remnants, and the chemical evolution of galaxies. You notice how the slow cooling and expansion carry clues about conditions within the merger, bridging observations and simulations. You watch as the neutron stars collide, releasing more than just light and gravitational waves. Among the streams of energy are neutrinos, nearly massless particles that interact only weakly with matter. They escape from the hot, dense interior almost unhindered, carrying a direct imprint of the physical conditions inside the merger. You notice that billions of these particles pass through every square centimeter of your body each second, yet they barely interact, emphasizing their ghostly nature. The production of neutrinos begins almost immediately. High temperatures and densities in the merger drive nuclear reactions, including beta decay and electron capture, that generate vast numbers of electron neutrinos and antineutrinos. These reactions release energy, heat surrounding matter, and contribute to the nucleosynthesis of heavy elements. You follow the flow of neutrinos as they carry away energy, allowing the core to cool slightly while conveying detailed information about pressure, density, and temperature at scales far beyond laboratory capability. Neutrinos are extraordinarily difficult to detect because they interact via the weak nuclear force. Most pass through planets, stars, and even dense neutron matter without scattering. You consider how only a tiny fraction of these particles are captured by large, sensitive detectors. Observatories like Super Kamiokande in Japan use massive volumes of water to observe Cherenkov radiation when a neutrino interacts with a nucleus, producing a faint flash of light. IceCube in Antarctica uses clear ice to detect similar signals across a cubic kilometer, recording the rare events when neutrinos finally collide with atomic nuclei. The energy spectrum of neutrinos provides information about the processes occurring in the merger. Low-energy neutrinos are produced by thermal processes in the hot matter, while higher-energy neutrinos result from more violent nuclear interactions. You notice how the distribution of energies reflects the temperature, density, and neutron richness of the ejected matter. Scientists can reconstruct these physical conditions by analyzing the detected neutrino flux and energy spectrum, linking observation directly to theoretical predictions. Neutrinos also reveal the rate at which matter cools in the aftermath of the merger. As the dense remnant evolves, neutrino emission dominates energy loss in the early phases. The rate at which neutrinos escape affects the pressure support inside the remnant, influencing whether it remains stable as a hypermassive neutron star or collapses into a black hole. You sense the subtle feedback between neutrino emission and the evolution of extreme matter, a process that unfolds in milliseconds yet is captured in precise simulations. The flavors of neutrinos, electron, muon, and tau undergo oscillations as they travel through space. You consider how these quantum phenomena allow one type of neutrino to change into another over long distances, providing additional layers of information. Observations of neutrino flavor ratios from distant astrophysical events can test fundamental physics, including the properties of neutrino mass and mixing angles. You realize that even these elusive particles carry both astrophysical and particle physics information across the universe. Neutrino detection complements gravitational wave and electromagnetic observations. While gravitational waves reveal the orbital dynamics and masses of the merging stars, and electromagnetic signals show ejecta composition and light emission, neutrinos probe the conditions inside the remnant. You sense how multi-messenger astronomy unifies these channels, each messenger providing unique and independent confirmation of the underlying physics. A single detection can validate models of nuclear reactions, extreme densities, and neutrino transport, bridging theoretical predictions and experimental observation. Timing is crucial. Neutrinos arrive at Earth nearly simultaneously with gravitational waves, slightly earlier than light from the kilonova because photons must diffuse through the expanding ejecta. You follow how this timing difference allows scientists to constrain the size, density, and opacity of the ejected matter. Observing neutrinos alongside other signals provides a natural clock, revealing the sequence of events with millisecond precision. You notice the remarkable synchronization across multiple observational platforms, linking particles, waves, and photons from a single astrophysical event. The total energy carried away by neutrinos is immense. In some cases, up to 10 to the power of 53 ergs, roughly comparable to the energy output of a supernova. You follow how this energy influences the evolution of the remnant, cooling it and allowing the dense core to adjust dynamically. The emission also contributes to driving winds in the surrounding material, affecting the ejected mass and its composition. Neutrinos, though weakly interacting, are essential actors in the physics of mergers, regulating both energy transport and matter distribution. You notice the historical significance. The first detection of neutrinos from a cosmic event occurred in 1987 from a supernova in the Large Magellanic Cloud, confirming theoretical models of core collapse. Neutron star mergers, although more challenging to detect due to distance and rarity, offer similar opportunities. You sense the quiet patience of science, relying on rare events to validate models and refine understanding. Detected neutrinos carry clean, nearly unaltered information from the interior, allowing researchers to test fundamental physical laws under conditions far beyond Earth's laboratories. The study of neutrinos also informs nuclear physics. Their interactions with matter are sensitive to weak force coupling, neutron-to-proton ratios, and nuclear cross-sections. By comparing detected fluxes and energies with simulations, scientists improve models of neutrino transport, beta decay rates, and dense matter behavior. You follow the delicate interplay between particle physics and astrophysics, seeing how the tiniest, most elusive particles illuminate the largest, most energetic events in the universe. Even after the merger, neutrinos continue to escape from the remnant for seconds or minutes, gradually carrying away residual thermal energy. You feel the persistence of these particles, silently streaming across space, reaching detectors on Earth long after the light from the collision has faded. Their journey is uninterrupted by matter, a constant messenger of processes that occurred in extreme densities and temperatures, traveling vast distances to inform our understanding of both the universe and the fundamental forces within it. You watch as the central remnant of the neutron star merger evolves under extreme gravity. Its mass is immense, concentrated within a radius of only tens of kilometers. The remnant's fate depends on the total mass, rotational support, and internal pressure provided by neutron-rich matter. If the combined mass exceeds the maximum sustainable limit for a neutron star, gravity overwhelms all forms of pressure, and collapse into a black hole becomes inevitable. You notice how each factor, mass, spin, thermal pressure, interacts according to precise physical laws to determine the outcome. Rotation plays a crucial role. Differential rotation allows the remnant to support more mass than a non-rotating neutron star would. You follow the way the inner regions spin faster than the outer layers, creating centrifugal support that temporarily counteracts gravity. This hypermassive neutron star can exist for milliseconds to seconds before rotation slows due to magnetic braking, gravitational wave emission, and viscous interactions. You sense the delicate balance between these forces, a fleeting stability before the final collapse. The collapse itself is governed by general relativity. As the core contracts, spacetime curves increasingly around it. You notice the formation of an event horizon, a boundary beyond which nothing, not light, not matter, not information, can escape. Inside this boundary, the density grows without bound, forming what theory predicts as a singularity. Observations cannot directly probe this region, yet gravitational waves, electromagnetic emissions, and neutrino signals allow scientists to infer its formation and properties. You consider the remarkable accuracy of Einstein's equations in predicting these extreme outcomes. Energy is released during the collapse. As matter falls inward, gravitational potential energy converts into heat, kinetic energy, and radiation. Magnetic fields are compressed and amplified, contributing to particle acceleration and relativistic jets. You observe how some of the surrounding material, particularly in the accretion disk, interacts with these processes, producing X-rays and gamma rays detectable across cosmic distances. The balance between infalling matter and outward energy release shapes the environment near the newly formed black hole. The accretion disk forms from material that retains sufficient angular momentum to orbit the remnant rather than falling directly into the event horizon. You notice the dynamics of this disk, heated to billions of degrees and generating intense radiation. Magnetic turbulence drives angular momentum transport, allowing matter to spiral inward gradually. The combination of rotation, magnetic fields, and relativistic gravity creates a complex environment where energy is converted efficiently, powering emissions and influencing the potential formation of relativistic jets. Jets can emerge along the rotational axis. These highly collimated streams of matter and radiation accelerate to nearly light speed. You follow how simulations demonstrate that magnetic fields and rotation geometry determine the structure, speed, and orientation of these jets. When aligned with Earth, they are observed as short gamma-ray bursts, confirming predictions about the connection between black hole formation and high-energy astrophysical phenomena. The energy scales involved are immense, equivalent to the combined output of a galaxy compressed into seconds. Gravitational waves provide a continuous signal throughout this process. The inspiral and merger produce a chirp, followed by high-frequency oscillations as the remnant stabilizes or collapses. You notice the waveforms encode information about mass, spin, and the stiffness of neutron-rich matter. If a hypermassive neutron star forms briefly, its oscillations modulate the gravitational signal, revealing the properties of ultradense matter before the final black hole emerges. These observations allow scientists to probe conditions inaccessible in any laboratory. Temperature and density reach extraordinary extremes. In the collapsing core, matter may reach several times nuclear saturation density, with temperatures of billions of degrees. You follow how thermal pressure initially slows the collapse, only to be overwhelmed by gravity. Nuclear reactions continue during this brief phase, contributing to neutrino emission, heating of the surrounding disk, and modification of electron fractions in the ejected matter. You sense how these processes are intertwined, shaping both the final black hole and the observable signatures in its environment. You reflect on the limits of neutron star stability. The equation of state, describing how matter behaves at supernuclear densities, determines the maximum mass a neutron star can support. Observations of mergers, gravitational waves, and electromagnetic counterparts refine these limits, providing empirical constraints on nuclear physics under extreme conditions. Each detection informs models, narrowing uncertainties about the internal structure, composition, and behavior of matter in the most extreme environments. The formation of the event horizon is sudden and definitive. Once it appears, nothing from inside can influence the external universe directly. You watch how the accretion disk continues to evolve outside the horizon, feeding matter into the black hole and producing persistent radiation. Relativistic jets may continue for seconds to minutes, carrying energy and momentum far from the remnant. You sense the distinction between what is observable and what is hidden beyond the horizon, appreciating how physics predicts both domains with remarkable precision. Energy balance remains central. The gravitational binding energy released during collapse exceeds the energy emitted in photons, neutrinos, and gravitational waves combined. You follow how the energy is partitioned. Some accelerates jets, some heats the disk, and some is radiated as neutrinos or gravitational waves. The remainder contributes to the mass of the black hole itself. You notice how theoretical models and simulations closely match observational data, confirming our understanding of these extreme processes. Time is relative in the vicinity of the black hole. You observe gravitational time dilation. Events near the horizon appear to slow dramatically when viewed from a distance. Light escaping from near the horizon is redshifted, and signals are delayed. You reflect on how general relativity accounts for these effects, predicting observable phenomena such as the gradual fading of radiation from infalling matter. These relativistic effects provide additional confirmation of Einstein's theory under extreme conditions. Even as the black hole forms, its influence extends far into space. Gravitational waves carry information about the collapse to distant detectors. Relativistic jets and radiation influence the surrounding interstellar medium. You sense how the formation of a single black hole affects both its immediate environment and the wider universe, linking microscopic nuclear interactions to large-scale astrophysical consequences. The interplay of gravity, rotation, and magnetic fields shapes both the remnant and the signals it emits. You notice the universality of these processes. Despite the extreme conditions, the laws of physics remain consistent. General relativity, nuclear physics, and electromagnetism govern the dynamics without deviation. The formation of a black hole is a predictable outcome once the parameters mass, spin, and equation of state are known. Observations confirm theoretical predictions, demonstrating the precision and reliability of physical laws even in the most extreme environments imaginable. You sense the energy of the neutron-star merger spreading outward, extending far beyond the immediate vicinity of the collision. Gravitational waves ripple through spacetime, traveling at the speed of light, distorting distances by infinitesimal amounts as they pass. You notice that these ripples carry detailed information about the mass, spin, and dynamics of the colliding stars, effectively broadcasting the event across the universe. Their effects are subtle but measurable, detectable by instruments sensitive to changes smaller than a proton's diameter. High-energy photons accompany these waves. Gamma rays, X-rays, and ultraviolet photons travel vast distances, conveying information about the energy release, ejecta composition, and orientation of the merger. You observe how electromagnetic signals are influenced by intervening matter, redshifted as they traverse expanding space. These signals complement gravitational waves, providing both timing and spectral information that allow astronomers to reconstruct the sequence of events with remarkable precision. Gravitational wave detectors, such as LIGO and Virgo, record the tiny stretching and squeezing of spacetime caused by the passing waves. You follow the methodical calibration and signal analysis that allows scientists to separate these cosmic signals from terrestrial noise. Each detection provides a direct measure of the distance to the source, the masses of the neutron stars, and the details of their orbital decay. You appreciate how these subtle ripples encode fundamental astrophysical information, revealing processes that occurred millions of light years away. The ripples also allow you to probe the expansion of the universe. By comparing the distance inferred from gravitational waves with redshift measurements of the host galaxy, scientists can refine estimates of the Hubble constant. You notice how these measurements complement traditional techniques, providing independent confirmation of cosmic expansion rates. Each wave carries a precise timestamp of the event, connecting local observations to universal scales and linking nuclear, stellar, and cosmological processes. High-energy photons from the merger travel through interstellar and intergalactic space, interacting occasionally with gas and dust. You observe that some gamma rays are absorbed and re-emitted at longer wavelengths, while X-rays may scatter or produce secondary particles. These interactions reveal information about the density, composition, and structure of the intervening medium. You sense the universe acting as both a conduit and a filter, allowing scientists to infer conditions across vast distances by studying how signals are modified on their journey. The combination of gravitational waves and electromagnetic signals defines multi-messenger astronomy. You notice how detecting both types of signals from the same event enhances understanding of the physics involved. Gravitational waves probe the dynamics of the merger and the internal structure of neutron stars, while electromagnetic observations reveal ejecta composition, energy release, and radiation mechanisms. Together, these observations validate theoretical models, constrain equations of state, and confirm nucleosynthesis pathways. Neutrinos, traveling nearly unimpeded, add a third messenger. Although challenging to detect, they carry information about the hottest, densest regions of the merger. You consider how combining neutrino detection with gravitational and electromagnetic signals offers a complete picture of the event, allowing scientists to study processes invisible to conventional telescopes. These ghostly particles provide unique insight into extreme nuclear physics, complementing the information carried by light and spacetime ripples. Cosmic distances stretch these signals in time. Photons from distant mergers arrive minutes, hours, or even years after the gravitational waves. You follow how scientists account for redshift, cosmic expansion, and propagation effects to reconstruct the original event accurately. The coordination of detectors worldwide allows precise timing and localization of sources, ensuring that the ripples and light are analyzed together. Each measurement adds detail to the cosmic narrative, confirming both the physics of neutron star mergers and the large-scale structure of the universe. You notice that the waves themselves provide information about fundamental physics. The waveform's shape depends on general relativity, the internal composition of neutron stars, and the dynamics of the merger. Deviations from predicted patterns could reveal new physics, but so far, observations are consistent with Einstein's equations. You follow how scientists use these signals to test gravitational theory under extreme conditions, probing spacetime in regimes unattainable in laboratories on Earth. The high-energy photons also allow spectroscopy, revealing the chemical composition of the ejected matter. Light spreads across the spectrum, from blue to infrared, depending on element abundance and expansion velocity. You observe how the intensity and color evolution over time inform models of our process nucleosynthesis, linking the formation of heavy elements to the observable universe. Each spectral line is a fingerprint, a direct connection between nuclear physics and astrophysical observation. Gravitational waves from mergers act as standard sirens, analogous to standard candles in traditional astronomy. You notice how the amplitude of the wave encodes the distance to the source, while the frequency evolution indicates mass and spin. By comparing distances to redshifts, you refine cosmological models and gain independent measures of the Hubble constant. The information encoded in these ripples reaches across time and space, linking the violent processes of compact object collisions to the large-scale behavior of the cosmos. You follow how these signals inform matter distribution in the universe. Gravitational waves are minimally affected by intervening matter, providing clean probes of spacetime. In contrast, photons interact with gas and dust, revealing the structure and composition of galaxies and intergalactic space. The combination allows reconstruction of both the source properties and the environment it inhabits. You sense how the universe preserves a record of events in multiple channels, each messenger revealing different layers of information. Even as the signals travel billions of light-years, they retain subtle details about the merger's orientation, the mass ratio of the stars, and the presence of jets. You notice how astronomers analyze patterns in arrival times, polarization, and spectra to reconstruct the event's geometry and energetics. Each ripple, each photon, carries a coded record of the physical laws at play, offering a remarkable opportunity to study physics in its most extreme form. You appreciate the coherence of the universe's communication. Gravitational waves ripple silently through spacetime. Photons illuminate composition and energetics, and neutrinos whisper the secrets of extreme densities. Together, they allow precise reconstruction of events that occurred across unimaginable distances. You sense the universe as a network of connected phenomena, where local physics informs cosmological understanding and every signal contributes to a larger map of cosmic history. You watch the remnants of the neutron star merger slowly expand into the surrounding interstellar medium. The ejected matter, rich in heavy elements like gold, platinum, and uranium, moves outward at tens of thousands of kilometers per second. Over time, the material begins to interact with clouds of gas and dust, colliding gently and mixing under the influence of gravity, turbulence, and magnetic fields. You notice that this process is gradual, occurring over thousands to millions of years, yet it plays a critical role in shaping the chemical composition of future stars and planets. The expanding ejecta carries both energy and momentum. As it collides with interstellar gas, shock waves propagate, compressing and heating the surrounding medium. You follow how these shocks trigger density fluctuations within the gas clouds, creating regions that may eventually collapse to form new stars. The enrichment of these clouds with heavy elements from the merger adds complexity to the chemistry, allowing for more diverse planetary compositions. Each passing year redistributes matter across light years, a silent contribution to the ongoing cycle of star formation. You observe how different elements mix at different rates. Lighter elements, such as carbon, oxygen, and iron, integrate more easily into existing clouds, while heavier R-process elements may remain concentrated in small clumps initially. Turbulence and stellar winds gradually distribute these elements more evenly. You sense the cumulative effect. Every neutron star merger subtly shifts the elemental makeup of its host galaxy, seeding future stellar systems with rare nuclei that were absent in the primordial gas. Molecular clouds, the nurseries of stars, absorb this enriched material. You follow how regions of higher density within these clouds collapse under self-gravity, forming protostars. The surrounding disk of gas and dust captures heavy elements, which later contribute to planet formation. You notice that the presence of R-process elements affects mineralogy and potential planetary chemistry, linking events billions of light-years away to the materials that will eventually compose terrestrial worlds. The distribution of heavy elements also influences stellar evolution. Stars that form from enriched clouds can have higher metallicities, affecting their opacity, energy transport, and lifetimes. You observe that even small increases in the abundance of heavy nuclei alter nuclear reaction rates in stellar cores, subtly shifting the star's evolution. Over cosmic timescales, the cumulative effect of mergers, supernovae, and stellar winds gradually changes the chemical landscape of galaxies, creating diversity in stellar populations and planetary systems. You notice that neutron star mergers are relatively rare, yet their impact is disproportionate. Each event ejects masses of neutron-rich material sufficient to explain a significant fraction of heavy elements observed in the galaxy. When combined with supernovae, these mergers account for the full spectrum of nucleosynthesis products, ensuring that elements necessary for planets, chemistry, and life are available in subsequent generations of stars. You sense the quiet efficiency of the universe in recycling matter across epochs. Cosmic recycling is aided by galactic dynamics. You follow how differential rotation of the galaxy stretches and shears enriched material along spiral arms, dispersing it over vast distances. Supernovae and stellar winds continue to stir the interstellar medium, mixing merger ejecta with older gas. Over millions of years, the once concentrated material from the collision becomes part of a diffuse, chemically enriched reservoir, ready to participate in the next cycle of star formation. You appreciate the interconnectedness of these processes, linking the violent and the serene. You watch how dust grains within the ejecta provide surfaces for chemical reactions. Ices and minerals accumulate heavy elements, forming small solid particles that survive within molecular clouds. These grains catalyze the formation of simple molecules, such as water and carbon monoxide, and eventually more complex compounds. You notice that this microscopic aspect of cosmic recycling complements the large-scale dynamics, bridging atomic physics, chemistry, and astrophysics in a continuous cycle of material transformation. The timescale of enrichment is long. The matter ejected from a single merger may take millions of years to be incorporated into new stars. You follow simulations showing how clouds gradually absorb heavy elements, allowing astronomers to predict metallicity patterns in different regions of galaxies. Observations confirm these patterns, indicating the cumulative influence of multiple mergers and supernovae over billions of years. You sense the quiet patience of cosmic processes, where even dramatic collisions unfold consequences over timescales far beyond human experience. You notice that star clusters forming from enriched clouds can inherit unique chemical signatures. Spectroscopic observations reveal variations in element abundances, including R-process elements, allowing scientists to trace the history of mergers in the galaxy. You follow how these measurements connect present-day stars to events that occurred long before the solar system formed. The chemical legacy of neutron star mergers is preserved in stellar atmospheres, providing a historical record of extreme physics and the distribution of elements across the Milky Way. Planet formation benefits directly from this enrichment. Protoplanetary disks incorporate heavy elements from the surrounding cloud, influencing the composition of emerging planets. You observe how cores of terrestrial planets may accumulate significant quantities of rare elements, shaping their magnetic properties, geology, and potential habitability. The materials dispersed by ancient mergers ultimately contribute to the diversity of worlds, connecting stellar catastrophes to planetary evolution and, in turn, the conditions necessary for life. You also note the influence on the broader galactic ecosystem. Enriched gas may trigger star formation in neighboring regions, propagating waves of chemical evolution across the galaxy. Each merger contributes incrementally, yet collectively these events maintain the continuous enrichment of the interstellar medium. You sense the quiet rhythm of matter cycling, driven by gravity, nuclear physics, and stellar processes, steadily transforming the chemical character of the galaxy over billions of years. The interplay between mergers, supernovae, and stellar winds ensures the universe remains chemically dynamic. Heavy elements from neutron star collisions integrate seamlessly with materials from other sources, producing a rich tapestry of matter ready for future generations of stars, planets, and potential life. You reflect on the slow but persistent transfer of energy and matter across scales, connecting violent cosmic events to the formation of stable, life-supporting systems. You begin by considering the inherent difficulty in observing neutron star mergers. These events are rare, unpredictable, and often occur at distances of millions or billions of light-years. Despite their energy, much of the activity occurs in regions invisible to the naked eye or traditional telescopes. You notice how astronomers have developed specialized instruments to capture signals across different channels, including gravitational waves, electromagnetic radiation, and neutrinos. Each detection provides a distinct perspective on the physics of the merger. Gravitational wave observatories, such as LIGO in the United States and Virgo in Europe, detect minute distortions in spacetime. You follow the process. Laser interferometers measure the stretching and squeezing of space, with precision smaller than a proton's diameter. These observatories record the characteristic waveform of two neutron stars spiraling inward, merging, and settling into a remnant. The timing and amplitude of the waves allow scientists to infer masses, spins, and the distance to the event with remarkable accuracy. Gravitational waves are complemented by electromagnetic observations. You watch as gamma-ray telescopes detect bursts of high-energy photons lasting less than 2 seconds, known as short gamma-ray bursts. These bursts provide immediate localization of the event and confirm the presence of relativistic jets produced during the merger. Following the initial burst, optical, infrared, and X-ray telescopes monitor the evolving light from the kilonova. You notice how the fading luminosity, color changes, and spectra reveal details about the ejected matter's composition and velocity. The coordination required to capture these signals is precise. Observatories must respond quickly to alerts from gravitational wave detectors, often within seconds to minutes. You follow how telescopes worldwide adjust their fields of view, capturing light from the transient event before it dims beyond detectability. Multi-wavelength observations, from radio to gamma rays, ensure a comprehensive picture, revealing both the dynamics of the merger and the nucleosynthesis occurring in the ejected material. Neutrino detectors add another layer of observation. Instruments such as Super Kamiokande in Japan and IceCube in Antarctica monitor massive volumes of water or ice for the rare interactions of neutrinos with atomic nuclei. You consider how these ghostly particles carry unaltered information from the densest regions of the merger. While detections are infrequent, each successful measurement provides a direct probe of the extreme temperatures and densities inside the remnant. You observe how data from different messengers are combined. Gravitational waves provide precise timing and mass information, electromagnetic signals reveal composition and energetics, and neutrinos probe internal conditions. Scientists integrate these datasets to construct a coherent understanding of the event. You notice that this multi-messenger approach has revolutionized astrophysics, allowing verification of theoretical models and refining predictions about neutron star behavior, nucleosynthesis, and relativistic phenomena. Telescopes use a variety of techniques to extract information from light. Photometry measures the brightness over time, producing light curves that track the kilonova's evolution. Spectroscopy divides light into constituent wavelengths, identifying elements and isotopes in the ejecta. Polarimetry measures the orientation of light waves, revealing asymmetries in the explosion or alignment of magnetic fields. You follow how each method adds a layer of understanding, allowing scientists to probe both the physics and geometry of the merger. Distance and localization are crucial. Gravitational waves alone provide approximate directions, often spanning tens to hundreds of square degrees. You notice how optical surveys narrow this region by identifying transient sources consistent with merger predictions. Follow-up observations across multiple wavelengths confirm the identification. Precise localization allows measurements of host galaxy properties, redshift, and environment, which are essential for understanding how mergers contribute to cosmic chemical evolution and testing models of matter under extreme conditions. You notice the importance of simulations in interpreting observations. Numerical relativity and hydrodynamics models predict gravitational waveforms, ejecta velocities, and nucleosynthesis outcomes. Observational data are compared with these simulations, refining parameters such as the equation of state of dense matter, maximum neutron star mass, and the behavior of matter in extreme magnetic and gravitational fields. You sense the continuous feedback between theory and observation, where each event improves the accuracy of predictions for future detections. The technology and scale involved are remarkable. Gravitational wave detectors require kilometer-scale interferometers, vibration isolation, and laser stabilization to detect spacetime distortions. Space-based telescopes observe high-energy photons above Earth's atmosphere, while neutrino observatories rely on cubic kilometers of natural material for detection. You follow the global coordination among observatories, data centers, and research teams, reflecting the complexity of capturing fleeting signals from such rare events. Observing these events also informs fundamental physics. Deviations from predicted gravitational waveforms could indicate new physics or constrain alternative theories of gravity. The relative timing of photons, neutrinos, and gravitational waves tests the speed of light and neutrinos over cosmological distances. You notice how each detection provides a laboratory for physics under conditions impossible to recreate on Earth, revealing the deep connections between astrophysics, particle physics, and cosmology. You observe the refinement of methods over time. Initial detections required painstaking data analysis to separate signals from noise, while modern pipelines provide real-time alerts, enabling rapid follow-up. You follow how this evolution allows scientists to capture events from their earliest phases, maximizing the information gathered. Each observation contributes to a growing archive, enabling statistical studies of neutron star mergers, event rates, and their contribution to chemical evolution. Even after the immediate signals fade, careful analysis continues. You notice how archival data from previous observations are re-examined in light of new detections, confirming patterns, refining models, and occasionally revealing previously unnoticed events. Multi-messenger astronomy allows scientists to reconstruct the full life cycle of these mergers, from inspiral and collision to kilonova and eventual black hole formation. You sense the meticulous, persistent work that turns fleeting cosmic events into lasting scientific knowledge. The observations also connect to broader cosmic questions. You follow how gravitational wave detections provide distances to mergers, aiding in measurements of the Hubble constant. Electromagnetic and neutrino data reveal how matter behaves under extreme conditions, informing nuclear physics and astrophysics. Each event, though rare, provides a window into the universe's behavior at its most energetic and extreme. You sense the cumulative impact of these observations, gradually building a detailed map of cosmic evolution and the role of neutron star mergers in shaping galaxies. You begin by reflecting on the fundamental laws tested during a neutron star merger. These collisions occur under extreme gravity, density, and temperature conditions, far beyond anything reproducible on Earth. General relativity, nuclear physics, and electromagnetism are all simultaneously at work, governing matter and energy in the most extreme regimes. You observe how the merger provides a natural laboratory for physics, where the interplay of forces and interactions can be studied through the signals that reach Earth. Gravitational waves offer a direct test of general relativity. You notice how the waveform encodes information about the masses, spins, and orbital dynamics of the neutron stars. By comparing observed waveforms with theoretical predictions, scientists can confirm or constrain deviations from Einstein's equations. Each merger provides a unique dataset, and repeated detections allow increasingly stringent tests. The agreement between observation and theory reinforces the robustness of our understanding of gravity under extreme curvature. Neutron star interiors are composed of ultradense nuclear matter, with densities exceeding those found in atomic nuclei. You follow how these conditions allow scientists to explore the equation of state, the relationship between pressure, density, and temperature inside the star. Observed gravitational waveforms, along with electromagnetic and neutrino signals, provide constraints on this equation. You notice how subtle differences in waveform shape, peak frequency, and damping reveal whether matter behaves more stiffly or softly, indicating how neutrons interact under intense pressure. Collisions also illuminate our process nucleosynthesis. You observe how heavy elements, from gold to uranium, form in the high-density neutron-rich ejecta. Understanding these processes requires knowledge of nuclear reaction rates, neutron capture cross-sections, and beta decay under extreme conditions. Observations of kilonova light curves and spectra validate these models, confirming that neutron-star mergers are primary sites for heavy element production. You sense the direct link between nuclear physics and astrophysical phenomena, where laboratory measurements connect to events occurring millions of light-years away. Magnetic fields play an essential role in shaping the post-merger environment. You follow how differential rotation amplifies magnetic fields to strengths of 10 to the power of 15 Gauss or higher, influencing the structure of the remnant, jet formation, and energy transport. These fields also affect the emission of electromagnetic radiation and the acceleration of particles in relativistic jets. Observing the consequences of these fields provides empirical input for magnetohydrodynamic models, linking theoretical physics to observable phenomena. Neutrino emission offers additional insights. You notice that neutrinos carry information about the temperature, density, and composition of the merger remnant. Detected fluxes and energy distributions allow scientists to refine models of neutrino transport, weak interactions, and cooling processes. These observations, combined with gravitational waves and electromagnetic data, give a more complete picture of matter under extreme conditions. Neutrinos act as messengers of the fundamental interactions governing the merger, providing unique constraints on nuclear physics. You observe how these events challenge high-energy astrophysics. Short gamma-ray bursts, relativistic jets, and kilonova emissions test models of radiation transport, particle acceleration, and relativistic hydrodynamics. By comparing simulations with observations, scientists refine their understanding of energy conversion and the mechanisms by which compact object mergers generate observable light across the electromagnetic spectrum. Each event helps confirm or adjust theoretical frameworks, linking high-energy phenomena to the underlying physics of matter and gravity. The timing of signals provides precise tests of fundamental constants. Comparing arrival times of gravitational waves, photons, and neutrinos constrains differences in their propagation speeds. You notice that these measurements confirm that gravitational waves travel at the speed of light within extremely small margins of error. Such constraints provide confidence in the universality of fundamental laws and narrow the parameter space for alternative theories of gravity. Each merger detection contributes to our understanding of spacetime and particle physics on cosmological scales. Observations of merger remnants also reveal information about neutron star stability limits. You follow how mass thresholds determine whether a remnant collapses immediately into a black hole or forms a temporary hypermassive neutron star. By combining observations from multiple events, scientists refine estimates of maximum neutron star mass and the stiffness of nuclear matter. This, in turn, informs models of supernova remnants, stellar evolution, and the demographics of compact objects across the universe. You sense the precision with which physical theory, informed by observation, defines what is possible in nature. Cosmology benefits as well. Gravitational wave observations act as standard sirens, providing independent measurements of cosmic distances. You notice how combining these distances with redshift data refines estimates of the Hubble constant, offering insight into the expansion rate of the universe. Each detection contributes to a growing understanding of cosmological parameters, allowing scientists to connect extreme astrophysical phenomena with the large-scale structure and evolution of the cosmos. You observe the integration of multiple disciplines. Nuclear physics, general relativity, high-energy astrophysics, and observational astronomy converge to produce a coherent understanding of mergers. Models are refined continuously through the interplay of theory, simulation, and observation. You sense the rigorous methodology at work. Predictions tested, discrepancies analyzed, and theories adjusted. The merger events serve as a bridge connecting microphysics of nuclear matter to macroscopic astrophysical processes. Even fundamental questions, such as the behavior of matter at supernuclear densities, find experimental grounding through mergers. You follow how waveforms, light curves, and spectral data constrain internal pressures and neutron interactions. Each event provides empirical data that can support or challenge competing nuclear models. This direct observational input is rare, as terrestrial experiments cannot reach these densities, making neutron-star mergers indispensable for advancing nuclear and particle physics. You notice that every observed merger gradually builds a database of extreme physics. Patterns emerge, allowing statistical inferences about mass distributions, spin orientations, merger rates, and element production. By carefully comparing observations with predictions, scientists validate theories ranging from relativity to nuclear reaction networks. Each event, though brief in duration, contributes enduring knowledge about the fundamental forces shaping the universe. The study of neutron star mergers highlights the interconnectedness of physical laws. Gravity governs orbital decay and collapse. Nuclear physics determines internal pressure and element formation. Electromagnetism shapes radiation and particle acceleration, and neutrinos carry unaltered information from dense cores. You sense how each aspect complements the others, forming a self-consistent framework that explains phenomena from the smallest scales to the cosmic. Observations continually confirm that these laws apply universally, even under conditions far beyond everyday experience. You watch the aftermath of the neutron star collision as the immediate chaos gradually fades into quiet. The remnant, whether a black hole or a hypermassive neutron star, stabilizes over seconds to minutes, while the ejected matter expands outward into the surrounding space. Shock waves dissipate, and high-energy radiation decreases, leaving the cosmos momentarily calm. You notice how the signals from this distant cataclysm continue traveling through the universe, carrying information about the event across millions or even billions of light-years. The gravitational waves propagate silently through spacetime, stretching and compressing distances ever so slightly as they move outward. You follow how these waves pass through galaxies, clusters, and vast cosmic voids, unaffected by dust or gas. Their presence is imperceptible without specialized detectors, yet they carry precise records of the masses, spins, and dynamics of the original stars. These ripples are lasting messengers of the merger, quietly documenting the most extreme events in the universe. Matter ejected from the merger continues to expand and cool. The R-process elements, including gold, platinum, and uranium, mix gradually with the interstellar medium. You notice how turbulence, magnetic fields, and interactions with existing gas and dust clouds disperse these heavy elements across light-years of space. Over time, the enriched gas becomes part of the galactic environment, slowly contributing to future star formation and planetary systems. You sense the patient, methodical recycling of matter that occurs on timescales far longer than human perception. High-energy photons, initially emitted in intense bursts, fade over days to weeks. You watch as X-rays, ultraviolet light, and gamma rays diminish in intensity, leaving longer wavelength emissions, including optical and infrared, that linger for weeks. Observations of this fading light allow astronomers to study the composition, velocity, and geometry of the ejected material. Each photon reaching Earth carries a snapshot of the violent processes at the time of the merger, a record of temperatures, densities, and nuclear reactions occurring in the kilonova. The surrounding interstellar medium gradually absorbs the kinetic energy of the ejecta. Shock fronts slow as they transfer momentum to gas clouds, and regions of higher density begin to form. You follow how these compressed pockets may become sites for future star formation. The heavy elements from the merger enrich these clouds, influencing the metallicity of new stars and their potential planetary systems. You sense the subtle, long-term influence of the merger, as its products integrate into the galactic environment over millions of years. Neutrinos, having escaped almost immediately, continue to travel unimpeded. You notice that these nearly massless particles carry information about the densest, hottest regions of the merger. While most pass unnoticed, detectors on Earth occasionally capture a few, confirming models of extreme nuclear physics. These observations complement gravitational wave and electromagnetic data, providing a more complete understanding of the processes occurring in the densest regions of the universe. You reflect on the integration of all these messengers. Gravitational waves, photons, and neutrinos collectively record the event, each carrying distinct but complementary information. Scientists use these signals to refine models of neutron star structure, nuclear reactions, and relativistic dynamics. Each observation strengthens the connection between theory and reality, offering rare insights into processes that cannot be replicated in any terrestrial laboratory. Over cosmic time, the merger's influence extends beyond its immediate surroundings. The dispersed heavy elements mix with existing gas, gradually homogenizing within the galactic medium. Future stars forming from this material inherit the chemical fingerprints of the merger. You sense that even though the event is brief, its contribution to the ongoing evolution of the galaxy is lasting, silently shaping the composition of stars, planets, and potentially life-bearing worlds. The black hole or hypermassive neutron star left behind may also have longer-term effects. If a black hole formed, it continues to influence nearby matter through gravity, possibly accreting leftover material and generating additional radiation. If a hypermassive neutron star persists, it may emit rotational energy, magnetic fields, and neutrino flux over seconds to minutes before collapsing. These remnants play a subtle role in distributing energy and momentum into the surrounding environment. You notice that each merger leaves a multi-layered record in the universe. Gravitational waves stretch across spacetime, photons illuminate the ejecta, neutrinos escape from the densest regions, and heavy elements slowly become part of new cosmic structures. You sense a quiet balance between the immediate violence of the merger and the gradual, persistent integration of its products into the cosmos. The event, though transient, contributes enduringly to the evolution of galaxies. Galactic recycling continues, as stars formed from enriched material carry forward the legacy of ancient mergers. These stars may go on to explode as supernovae, producing further heavy elements and distributing them into the interstellar medium. Over billions of years, the combined effects of neutron star mergers, supernovae, and stellar winds maintain a dynamic, evolving chemical environment. You observe how these processes collectively drive the enrichment of the universe, ensuring the ongoing diversity of elements necessary for complex structures and potential life. You reflect on the timescales involved. While the merger itself lasts mere seconds, its consequences unfold over millions or billions of years. Gravitational waves traverse the universe almost instantly. Light signals take years to reach observers, and matter disperses gradually into new star-forming regions. You sense the interplay of immediate, high-energy processes with slow, cumulative effects that shape galaxies over cosmic time. The universe quietly records these events, preserving evidence for future observers. Spectroscopic studies of stars reveal R-process elements, gravitational wave observatories detect ripples from distant mergers, and archival telescopes capture light from past events. You notice that each detection connects past cosmic events with present knowledge, allowing scientists to reconstruct histories of extreme physics and matter distribution across the universe. Even as the violent merger fades from direct observation, its fingerprints persist. You observe how each event subtly influences the galactic environment, the chemical composition of future stars, and the conditions for planet formation. The universe maintains a continuous record, where even fleeting cosmic catastrophes leave enduring traces, quietly shaping the physical and chemical evolution of galaxies. You sense the ongoing rhythm of the cosmos. Mergers occur sporadically, yet cumulatively they drive enrichment, energy distribution, and structural evolution. Gravitational waves ripple across the universe, photons illuminate distant ejecta, and neutrinos whisper from dense cores. The interplay of these processes weaves a persistent thread through space and time, connecting transient events to long-term cosmic development.